Okay, so we're going to talk about the laws of thermodynamics briefly in the next videos, but one aspect of thermodynamics is interesting to look at, and that's Newton's law of cooling. And what Newton discovered is that the bigger the difference in temperature between the object and the surroundings, the faster the rate of cooling, exponentially so. So what he found is that the rate of cooling of an object is proportional to the temperature difference between the object and its surroundings. So we're going to take a look at that and come up with a formula for it. So to do that, we're going to look at this sort of real-life example. And we have Jim at a summer job cooking up a big pot of soup late at night, so they'd have soup for the next day. But what he found is that while refrigeration was needed, the soup was too hot to be put directly into the fridge when it was ready. So the soup had just boiled at 100 and the fridge was not powerful enough to accommodate it if it was any warmer than 20 degrees Celsius. So what he had to do is to get the soup at 100 degrees Celsius, get it down to 20 degrees Celsius before it could go into the refrigerator. So just a little note about food safety, that's really necessary. You can't just take a big thing of food or soup that's just come out of the stove, put it in the refrigerator and think, well, it's good to go. Because the center of it will not cool down fast enough for food safety standards. So just something to think about. So what he knew he had to do is to take the soup, put the pan into a sink of cold water, keep the water running so that the temperature is a constant 5 degrees Celsius. So this is our ambient temperature of 5 degrees Celsius. We need to get it down to 20 degrees, but it starts out, the initial temperature is 100 degrees. So stirring occasionally, he could bring the temperature of the soup to 60 degrees Celsius in 10 minutes. So that's some data. We know Newton's law of cooling is not linear, so he can't just, do that simple calculation. But he does have some data here. He knows that it can get down to 60 degrees Celsius in 10 minutes. So the question is, well, how about 20 degrees Celsius? How long before it can get down to 20 degrees Celsius? So he's just wondering how long before closing time should we get the soup ready, get it into the sink so it can cool down, and put it in the fridge so we don't give food poisoning to everybody. Okay, so what we're going to do is to call the temperature at time t. The big T is the temperature, the little t is the time, the temperature of the soup at time t. We have our initial temperature T sub naught, 0 seconds at 100 degrees Celsius. We have the ambient temperature, the temperature in the sink at 5 degrees Celsius, so that's our ambient temperature. And we're going to go ahead and get this formula. I will bring out another real-life example that can happen. Coroners use Newton's law of cooling to try to do time of death calculations. So for instance, the initial temperature of the body was right around 98.6 before the person died. And once you die, you start to cool off. And so they can take the temperature of the body when they discover it. Sometimes you can have an ambient temperature. So this doesn't always work. So if you find a body in a park at dusk, the temperature is going down. This ambient temperature isn't staying constant. So that makes the calculation not as valid. So we do make some assumptions here when we talk about our ambient temperature of 5 degrees Celsius. But again, if we keep the water running, he keeps stirring, we can talk about this as our ambient temperature. Starts out at 100 degrees Celsius. The rate of change of the temperature with time, we can talk a little bit about integrating, and it's proportional to the temperature at time t minus the ambient temperature. So the rate of change of the temperature with time is proportional to whatever time we're taking that temperature minus the ambient temperature. So the bigger the difference between the temperature of the soup and the ambient temperature, the faster this rate of change is going to be. So we know the soup is cooling down. We could redo this for things that are heating up, but soup is cooling down, so the temperature at time t minus the ambient temperature is greater than 0. We are going to put a negative out here, and we're also going to put a k for a constant to not just make it proportional, but to make it equal. And so this is going to be called our rate constant k. And I need it to have a negative k. Our k will be positive, but we're having a decreasing function, so I'll put a negative there. K is based on a lot of things, like specific heat capacity, surface area, the material that we're talking about has a certain specific heat capacity. So K is dependent on a couple of different things. But it is our rate constant, and so we have to figure that out for a specific instance. So I'm going to do a little bit of algebraic manipulation. Divide by this, multiply by this, we get this. If we integrate both sides, and again, you don't need to have calculus to do this, but that's what's happening here. What's going to end up happening is 1 over x is the natural log of x. So I'm just going to take the natural log of t minus t sub a equals negative kt plus c. K is a constant. So we're going to now you don't need a calculus to do this. We're going to apply e to both sides. So when I say e natural log of this, it gets basically e natural log gets rid of, I'm sure a math teacher would say differently, but gets rid of that. And we just simply get t minus t sub a, t at temperature at time t minus ambient temperature, equals c times e to the negative kt. So then what I'm going to do here is talk about this constant c, and our constant c we are going to take to be t sub naught minus t sub a, and one of the reasons is that if I just have t sub naught, t at time 0, e becomes 1, and then it's just t sub naught. So if I want to change that, I'm going to subtract t sub a. So this is our law of cooling equation that we're going to use. Temperature at time t, whatever we're interested in, is equal to the ambient temperature plus the initial temperature of the object minus the ambient temperature times e to the negative kt. So let's take a look at our soup then. From the information, Jim had the soup initially at 100 degrees Celsius. The ambient temperature was 5 degrees, the difference between those and 95. And we come up with this, this equation, plugging it in, where temperature at time t is equal to 5 plus 95 times e to the negative kt. Now there's some data here. And after 10 minutes, Jim knows that the soup does cool to 60 degrees. He has some data. And so what we're going to say is, okay, at t is equal to 10 minutes, it's 60 degrees. So temperature at time t is equal to 5 plus 95 times e to the negative 10k. Now, what you're going to want to do is rearrange, solve for k. So what I'm going to do is subtract the 5 over and then divide the 95. So I'm going to end up with 55 divided by 95 equals e to the negative 10k. Now, to get rid of that, get rid of the e, what I'm going to do is I'm going to apply natural log to both of these sides. Okay, and definitely do that. Hit your natural log of 55 divided by 95. When I take the natural log of e, it just gets rid of that. So I'm going to get natural log of 55 over 95 equals negative 10k. So over here, what you're going to get is 0.55. When you take the natural log of 55 divided by 95, you should get 0.55. Divide by negative 0.55. Divide by negative 10, and you're going to get k is equal to 0.055. So I know that that's my rate constant. That's the rate that the soup is cooling down for whatever reason. So then what I can do is come in and say, okay, well, our original question here for Jim to finish this up is, hey, how long is it going to take for this to cool down? So Jim needs it to be 20 degrees. So if I need it to be 20 degrees, I don't know what the time is, but I do know the rate constant now. It's negative the k is 0.055. I'm going to find out this t. So again, what I'm going to do is subtract the 5, divide by 95. So I'm going to go 15 divided by 95 equals e to the negative 0.055t. Okay, and then apply the natural log to both sides. From there. And you're going to get a number here, the natural log of 15 over 95. You're going to divide it by negative 0.055 because that gets rid of that. You divide it by negative 0.055. Your t should be 34 minutes. So make sure that you can get t is equal to 34. So Jim needs to have the soup ready 34 minutes prior to the cooling process. Get it over there, get it into the sink, let the water run over it, stir it. It'll be 20 degrees at 34 minutes. Put it in the fridge, go on home. So thinking about this, some other things to think about. As you go for a long time, what happens? If I plug in t is 60, time is 60 minutes, what happens there? So take a second to go through that, although the worksheets are also, you're going to go through that in the worksheets. There's a lot of things that follow this pattern. Like I said, with the time of death calculations, you would measure the temperature of the body. You'd say, all right, what's the ambient temperature? Maybe the person died in an apartment that was at 70 degrees Celsius. What's the difference between the initial temperature and the ambient temperature? Well, most people are at 98.6, somewhere around there when they, living. So when they die, they start cooling immediately. So the difference between that and the ambient temperature. They have values of K for bodies, and then you can solve for T. Another thing to mention here, it doesn't matter what units you use as long as you're consistent, so that T, this K and this T could be in minutes, seconds, hours, whatever, years if you're doing nuclear decay. And you would just have this K as being 1 over that time frame. You're making some assumptions about the ambient temperature and that kind of thing too, so you have to realize that there are some assumptions no matter what you're doing here. But that's it, so try some worksheets, problems.